Yeah. So again, my name is Blake Joyce. I am currently the Assistant Director of Research Computing for the University of Arizona. I will be leaving in about 3 weeks. So this is one of my swung son kind of events. But through ResBazAZ, and I will likely be part of the research community at University of Arizona for a time yet. We still have a lot of collaborators here, still have grants, and so I don't suppose I'll be disappearing. When I say I'm the Assistant Director of Research Computing, really my group does 3 things. It provides consulting, free consulting for using the University of Arizona's supercomputers. Those are all centrally funded by the university. And it basically every researcher through their faculty, their research faculty member can get free time on the supercomputers. So it's a centralized resource that you can use for free. And the reason the university provides that resource is that they understand that if you provide a little bit of compute, especially to new faculty members, new researchers, and get them going in their research programs, that has a positive benefit in a feedback loop where they become successful, they get publications done, they don't have to worry about setting up servers when they walk in, because almost every research program these days has some amount of computing they do that's more than their laptops or more than their desktops. And so we've been lucky at the University of Arizona in that this group has been centrally funded for over 30 years. And I have the original 1986 proposal for creating this group, and I will pass that on to whoever's next in line for this position. But it's kind of an interesting read how people thought about computers in 1986 versus how we think about them now. So what you see here is the actual data center on this slide. That machine that we see there is Ocelote. That is now 5 years old as of June 1. And so we'll be taking that one down for the next month to actually update it, change it, and everything else. A year ago, we bought Puma, which is the newest supercomputer, and it's about 2 to 3 times, depending on how you do your calculations, bigger than Ocelote. So we have a very nice new supercomputer. We're going to be keeping all 3 of the supercomputers. We have Elgato, Ocelote, and Puma. But essentially, we have a lot of computing time for the research community. So my group has 3 consultants that answer questions and help people use those. I also have 2 stats consultants. So Mark and Mohammed have been doing stats consulting for 35 years for the university. And they can help you at any time with developing experimental designs. How do I do my statistical analysis? And they really excel at explaining the reasoning and the kind of the philosophy of stats as much as they do the actual analyses. And then I also have a data and visualization consultant who can help with interactive visualizations, kind of large scale or web-based visualizations. He's recently done a lot of AR and VR because it's what the community asked us to help out with. And we also interface with a lot of the groups around campus, the Catalyst Studios, where there's a data viz wall. So some bright and shiny day when we all go back to campus, that's a centralized resource. And so we work with the Catalyst Studios to provide computing and research support. There's also a holodeck being built. If you're interested in that, please ping me later on either the Slack channel or some other method. And it's about what it sounds like. It's a holodeck, like out of Star Trek. But more on that later. We also have a number of other kind of groups around campus that we work with. Certainly the library is a lot, but we wind up being kind of a portal for researchers to find the things they need to accomplish their research, in addition to providing these resources. So today we're going to be talking about the HPC, but I just want to provide context going forward that it's not just about computing. We actually are a resource in many other ways as well. And that's a large part of why I'm part of this community is, I kind of sit at the crossroads between IT and research. My background, I actually started as an ecologist, and then I realized I need to learn genetics. So I learned genetics, and then I realized I need to learn bioinformatics. So I learned that. And then I realized I need to learn coding and computing. So I learned that, and now I run supercomputers some number of years later. So I'm also a researcher, and so I understand, the struggle and everything that entails. So sometimes I'm just an ear to listen to other researchers, so feel free to reach out. And I also want to point out that Dima Shaislov is the one who actually made all these slides. I'm just using them today. He couldn't join us. So, this is not my work. This is his work. He's on my HPC consulting team. So, without further ado, what are we really going to talk about? So I'll first try to describe why you would want to use a high performance computer or an HPC, also known as supercomputers. We'll kind of talk about how they're structured because it's a little bit different than using the computer in front of you. And so just a little bit of that information can be really helpful when you get onto the system. We can either use the Linux shell or we can use Open on Demand, which is a web interface that's kind of point and click. I prefer Open on Demand, so we'll leave the shell stuff unless somebody really wants to learn that. We can submit jobs and play around with Jupyter Notebooks or RStudio on demand, and I can show you both or either. And then we'll talk a little bit about like what it's like to be on a shared resource, because we had 964 active users last year, unique users across the university from 100 different departments. And so anytime you log on to the HPC, there's 100 to 300 people on those machines with you. So you're never alone. But the downside is, you have to be mindful. It's like being, in a public space. You have to be a good user, and you have to be, not do things. So I'll point out some things that I did when I first started using the HPC that I've since learned don't do that. And we'll talk about that at the very end if we have time. And for sure, stop me at any point, either unmute. I'm monitoring the chat as well, but please ask questions as we go along, and I'll try to answer them the best of my ability. So again, why do we use the HPC, right? When I first got into bioinformatics, this is kind of how I felt, right? Like, oh, I've been doing lab bench work for 10 years, and like computers are so much faster than watching plants grow on a bench. So this is going to be way easy. And then about 6 months later, I still hadn't done a single analysis because I had to learn a lot of things. I had to learn the software. I had to understand how to do the computing. My laptop wouldn't actually work very well for the genetics questions I was asking. And so it was just I realized really quickly that I had to kind of start over and rethink my life with bioinformatics. So, the common problems I ran into when I started down this road was that, doing analyses just takes too long, right? And so one of the things that the HPC provides is a lot of compute for free that's a lot bigger than your laptop. So for instance, most laptops are 8 cores or maybe getting to be like 10 or 16 cores, depending on what manufacturer you're talking about, maybe a little bit more than that. The newest Puma, the newest supercomputer, has 96 cores per node and 500 gigabytes of RAM. And we've got a little over 215 of those. So if you can imagine, that is quite a bit bigger than even desktop computers you would buy and put in your lab or put on your home desktop and run analyses and things like that. So there's a lot of compute that you have access to, and that's just one of our 3 supercomputers. We have a little over 24,000 cores on Puma, all said. We also provide GPUs for free because machine learning and deep learning and many other analyses, image analysis especially, uses GPUs to speed up calculations. So we provide both. We have K20s on Elgato, a little over 200 of those, I think, or 180 now, something like that. We have 28 P100s on Ocelote, and we have right at 30 V100Ss, which are, until the A100 was released just recently, that was the fastest chip that NVIDIA made for enterprise use. So we have a lot of compute that's really fast, and it's just inexpensive. So the university fronts all that, and that's why they do it. But there's a lot of things available to you that you'll be able to scale up your analyses a lot easier than if you're trying to buy your own server and get it set up. I also ran into the issue that my analyses were just very, very big. So, for instance, on our central storage, every faculty group, every research group can get up to 20 terabytes of storage for free. We provide 500 gigs for each group that doesn't have a time limit associated with it. The 20 terabytes is on a rotating, what we call X disk, and we'll talk about that a little later. And it lasts for 300 days. And then, you just kind of start fresh every 300 days. But there's also, because all of the computing is really close to each other and it's networked really close to each other, you can actually take your tasks and split them up across the computer and use thousands or more cores at any given time, which is not really something you can do if you're on your laptop or you're on your desktop and you're trying to like talk to other things like cloud computing or whatever else. So there's the ability to really divide your tasks down. Arielle Gladstein was one of my first undergrads, and she had to do 18 million genetic simulations. And so we accomplished a fair amount of those on the HPC resources. So this was about 5 years ago. And otherwise, it would have taken 18 years on her desktop. And it was a nice desktop to do the work. So the running joke is she owes me 18 years for her life, but I'm not going to collect on that. And, there's also just like the sheer number, right? 18 million of anything analyses or even just like adding ones and zeros together is quite a lot. So we also provide a fair amount of cores that you can use simultaneously, you and your group, your research group. So we'll dig into any of those things. But these are kind of the three problems that we help solve. What does it look like? At some point we can actually get back to doing tours of the data center, but honestly, it's just a bunch of servers stuck together. So each of these like metal boxes is a server. In the case of Puma, that's where the 96 cores are and the 500 gigs for RAM. And they're all just connected together in a place, and the data center is chilled, and it's nothing to look at. But if you can see into the system of what's going on, we're calculating, we help calculate all of the images for the black hole. What was that, 3 years ago? We are doing, 8 or 9 million, universal simulations with Peter Baruzzi's group. We have people who use the system for genetics analysis and image analysis, and they do, hundreds of thousands of jobs or analyses a day. And so the systems on the outside are kind of boring looking. On the inside, they're doing all kinds of cool stuff from 100 different departments. We have researchers that are doing natural language processing that are like analyzing cancer mechanisms and proposing new cancer mechanisms from publications off of PubMed, because no human can read all 200,000 or 300,000 publications that come out about cancer every year. And just really interesting stuff. So, boring on the outside, really, really interesting on the inside. And that's all it is. It's just a bunch of clusters of computers all stuck together in racks. And so, I often thought about, if my laptop is kind of a sedan, a classic sedan, then a supercomputer is a really fast car. But actually, the way that I would propose you think about it is it's not actually a fast car. It is a fleet of regular cars, right? There are 23,000 cores on Puma. None of those cores are all that much faster than what you would have on your laptop. And in fact, some of the desktops are actually faster, but there are 23,000 of them. You cannot actually put 23,000 cores in any space that isn't cooled. When we first bought the machine, we literally could not turn it on until we had fans blowing cold air over the racks, because they would get so hot as soon as we turned them on, they would melt themselves. So it's really more about like the sheer number of things you can do on HPC than it is like how fast any one of the components is. And so that was one of the things that I kind of had to learn when I first got started into this world. So think of a fleet of cars rather than a single, or a single fast car. And, something that's a little bit different about the HPC, as I was saying before, on your laptop, you're the only one who has access to that. You're typing on your keyboard, on your screen, and the computing is happening right here in front of you. When we log on to the HPC, we're going to use your keyboard and your monitor in front of you, but we're going to a different place, and there's a bunch of other people hanging out in that same place doing work. So it's a shared machine. You're never alone on the HPC. So it's good to keep that in mind as you use the resource. Just remember, there's 200 other people trying to do their work too. So just be mindful of that. And sometimes the system is really busy and there's 350 people on it, and sometimes there's 100 people on it. It's not that busy at all. And every day is a little different because it is a communal space, and things change as people come and go and do work and things like that. Again, this is also, your laptop is a local thing. Everything about that laptop sits in front of you locally. When you log on to the HPC, that is somewhere else. It actually sits in the basement of the UITS building, or the computer center, which is at the corner of Mountain and Speedway on campus. So when we log in today, we're going to go from where I live, which is Grant and Alvernon, basically, and we're going to go all the way over to campus, and that's where all the computing will happen. And wherever you're logged in from, that same thing will happen. What's kind of cool about this is that means that anything that you have on the HPC and any analyses you're doing on the HPC can actually be done from anywhere. So for many years, I've joked that I'd like to work from Tahiti. I'm actually going to go do that, and I can log in to the HPC and do work and help people from the HPC in Tahiti. I've done this when I was, traveling, the United States back when we could do such things. And so, like, that's sort of the nice thing about a remote computer. Both HPCs and cloud computers tend to be somewhere else in the world. And no matter where you are in the world, give or take, you can access that and then, do your work still. And that can be really nice. I was a field ecologist for many years, and I would have killed to have been able to keep doing analyses when I was out in the Philippines doing work, or when I was out in Brazil doing work, whatever else. So I see that as a benefit. The downside to it is you have to remember that you're somewhere else. So anything you have on your laptop, files, folders, whatever, might not be on the HPC. You have to actually move it there before you can see it in that environment. And the same thing, if you have outputs that you want to see on your local computer, you'll have to move it off of the HPC to your local computer to do anything you want to do on your laptop or desktop or whatever. So just remember that it's somewhere else, and you have to move back and forth things back and forth. And then there's kind of two ways you can interact with the HPC. I use both quite a lot. And the first one, the one we'll look at today, is interactive jobs. Basically, that means whatever compute you're going to ask for on the supercomputer, you can actually interact with it, right? You should never use the definition, the word and the definition of it. There it is. You can actually go back and forth and say, hey, I want to do this, I want that. So when we jump onto on-demand and ask for a Jupyter notebook, or if we ask for, an RStudio environment or a MATLAB environment or whatever we're going to look at, you're on an interactive job on the HPC. It creates a bunch of compute, downloads RStudio or Jupyter notebooks or whatever you've asked for, and then gives you an interface that you can interact with, and I can type code, or I can run scripts, or I can do whatever. That's great if you just have like a single analysis you want to do, or if you have some scripts you're developing or whatever you're doing. But sometimes you need to do 1 million of things, or you need to do 10 million of things, or you need to do 100,000 things. And you don't really want to do that by hand interactively, right? That's where scripting comes in. And so batch jobs is the other way. And that's I have 10,000 files I want to analyze. Here's the script I want to use to analyze those 10,000 files. Just go do that. And I'm going to walk away, and I'm going to go over here and have a tea or something. And I'm going to come back in 7 days. So just, go for it, HPC. And so those are batch jobs, right? You literally give it a batch of things to do and you walk away. I like to call it rotisserie science, right? You just put something on the rotisserie and you walk away, and days later it's like, oh, it's cooked, perfect, and so, but both ways, depending on what you want to do on the supercomputers, both ways are equally feasible and useful ways to interact with it. But just remember that you can do it either way. So again, I'm going to kind of walk you through Ocelote, but all of our supercomputers are built pretty much the same way. So I'm going to walk you through the architecture there, but this will be true of Puma. This will be true of Elgato as well. So just as kind of a general cluster diagram. Can you all see my mouse? I always forget whether Zoom shows your mouse. You can, thank you. So, we sit here somewhere in the world. I'm in Tucson. You might be somewhere else, right? And we use our credentials and talk over the internet, and we're going to go log into the HPC, which is over here. So what actually happens is when we go to the website, Open on Demand, or if we go, and if if you like using the terminal, Shell or Unix, you can SSH to the computers that way too. But basically, the first thing you hit is what we call a bastion host. And a bastion host is just as it sounds. Bastion is like it's literally the same word derived from French. That is, it's a castle. It's kind of it's a wall around all the things that are HPC that shield it from the outside world. Hackers and malware and bots and all kinds of things that happen out there. So, as we log in today, you'll go on and you'll give it your net ID. You'll give it your net ID password, just like anytime you sign into anything at U of A. And then we do two-factor. So you'll, either use your phone to use Duo, or you'll do something else, whatever two-factor you use for your email or for whatever other systems you're logging into. Basically, that gets us into the login node. So, we're going to go from the bastion host, and when you're signing in on openondemand.hpc.arizona.edu, we'll do this in a little bit. This is kind of what it'll look like after you get past that bastion host. On the command line, it looks like this. There's a terminal. It'll have your username. So mine would be bjoyce3, but it would be whatever your U of A net ID is. And then it'll say you're on a login node or you're on some kind of computer, and it'll await a command. So the graphical interface from Open on Demand looks quite a bit different than if we were going to get onto a terminal. And we can look at both of those today and get comfortable with those. But that's what happens right after you get past the bastion host. What you're basically sitting on is the login node. And the login node is just that. Is after you've logged in, you're sitting on this thing, and that's where you're going to interact with the HPC. And we'll get into all this stuff. So the login node, if you're using the terminal, is really important to know that's where you are, because the login nodes can't do any analyses. And I will admit to my faults, but the very first thing I did when I jumped on the supercomputer is I saw this command line prompt, and I was like, yep, I'm bjoyce3, and look, I'm on the supercomputer, run an analysis. And that's not it, right? Like, all of the computing resources are over here. We haven't made it there yet. The login node itself is not even a computer. It's a virtual machine, and it's a very small one, and there's 200 people on that same one with you. So if you run an analysis on a login node, you're now making 199 other people very angry. And the thing about having your net ID out there in the world is they can find you, and no one does this, but it's good to be a good community member. So, just be mindful again that like login nodes are not for computing. The compute nodes are for computing. Well, I'll show you that here today. And I'm telling you, the very first time I logged in, I just started doing what I'm telling you not to. So I have done the wrong, and I understand it. So remember, if the supercomputers are the fleet of cars, there's 23,000 cars, a login node is a golf cart. And it is not something that you want to do. You're not going to get any analysis done because it's very, very, very small. It's even less than a CPU because we virtualize it. So your phone has more computing power than a login node does. We typically use the login nodes to move data around and then submit jobs if you're going to do in Bash or if you're going to do interactive jobs. And that's really all they're for, is just interacting with the computer and getting a compute node, whether you're going to do interactive compute node or you're going to do, you're going to say, I need you to do 10,000 of these jobs, take it away. And so just, that's what you use the login computer or login node for, is just submitting jobs. And we'll walk through that. And again, no calculations on there. And, it would be the equivalent of taking your golf cart out onto the highway. And you don't do that because it's dangerous, but it's also like it just inconveniences a lot of people on the highway. Running analyses on the login nodes is about the same. We've taken steps to help people understand that. And we've removed most of the software that was available on the login nodes, but there's no way to be 100% about these things. So it's always good to just remember no computing on the login nodes. And that's really the biggest thing. And I'll get off my soapbox now. But when we get onto the Linux shell, if we do that, we can do commands. And if you know Unix, you can do change directory. It's all the same things you're used to in a Linux or a Mac terminal kind of environment, Bash or Unix of any other type. You'll see a command, we'll put that in. This one tells you what user you are. And so it returns, this is the user I think you are. When you're talking to a computer, there's really specific commands that it understands, and there's structures to those commands. And we won't get into all the Unix things today, but I can answer some of those questions later on. If you ever need usage or need to know how to use a command, I like to Google everything. Some people like to use manual pages, but I'm a big fan of just Googling commands, and I still do that. And I've been doing this stuff for 6 years now, pretty consistently, and I still wind up Googling everything. So when in doubt, look it up, because that's what everyone else does too. But there's also options you can do called flags and things like that. And this is how a lot of people interact with the supercomputer. And many commands have this like help flag, so I like to point that out too. That can be useful. So, and actually, we might just jump on to Open on Demand before we get too far into this, because I'd like y'all to see what we're talking about here. Who here has an HPC account already? Okay, one thumbs up. Cool. Yeah. And that's going to change June 19th, Kiri, so get ready. I will lose all my things once I leave. Is there anyone that would like to get onto the supercomputers but doesn't have an account? You can also just watch me do it, and I'll walk you through it either way. But I'll share another screen here. So we're just going to log on, and we're going to see, because there's a lot of, that didn't help at all. There's a lot of other sessions that have been going on for Python and for Open on Demand. And I usually teach this on the second day, because this is actually a pretty good place to run all that stuff that you're starting to learn and to kind of continue working. So I'm going to do Open on Demand, od.hpc.arizona.edu. And you can follow along, and you can log into your own instance of this. Yeah, if you have an account from a long while back, Jay, it'll still be there. So you can try logging into Open on Demand, hpc.arizona.edu, if you would like. Or otherwise, you can just watch me. So when we go there, it's going to ask me for my credentials. So I'm going to type in my NetID and my password. My duo. And make this a little bigger so everyone can see. It's a fairly straightforward interface. I'm going to move some of this stuff around. This was created by a group funded by the NSF, if I remember correctly, and we really like it because the other option is to get onto the supercomputers using a Unix shell, and this is what it looks like. And I don't know about you, but it's been 25 years since I've seen a text adventure video game. There's a reason that we moved away from text adventure video games, because they're not quite as exciting as having, or useful for that matter, as having a graphical interface. But this is that environment. I can show you that I'm not on my local computer, because if you looked at your local computer on the Unix shell, you would have like my documents, and you'd have all the things in Mac and Windows and other operating systems present to you. Your desktop applications, et cetera, et cetera, et cetera. So what we're seeing here is, this is my NetID on the supercomputer. We have 2 login nodes on Puma, One's called Junonia and one's called Winteltrap. And it's a bit of an inside joke. Can anyone get it? I'll let you think about that one. I'll tell you here in a second. And so, you can tell pretty quickly that this is not your regular computer. I've got a bunch of like Python notebooks because I spin them up and show people things and forget to name them. I've been doing some NVIDIA container analysis and other things. So this is what that interface would look like. But if I wanted to do anything, I would have to do all these commands and texts, and that can be pretty difficult. I prefer very much using this interface because it's point and click, and that's way easier to use, generally speaking. And I don't have to remember anything special. So that's why we support Open On Demand and all that other stuff. So I can look at my files. As a user, I have a home directory, vJoyce3, that has 50 gigs in it, where I usually keep those. That's like where I keep like my outputs, or I keep, if I'm working on a script and I'm the only one who really needs to look at it because I'm still working on it and it's not quite ready to like put onto GitHub or to share with anybody else, I'll put it in the home directory. If every research faculty member gets a 500 gig group allocation, and that's shared across the entire research group that's signed up for the HPC. So if your PI has, 2 other students and you're the third person in a group on the HPC, that's a really good place to be able to share common files amongst everybody. So a lot of geneticists will put their reference genomes in that group's partition. NLP folks will put their corpori. I'll figure out that word someday. And they'll put that in the common place because that's all going to be common input for each of their analyses, and they're doing their own analyses, but they're using the same corpora. And XDisk is the temporary disk that you can ask for up to 20 terabytes on a rotating schedule of 150 days, up to 300 days. And so that's usually like if you have a lot of data that you need to analyze within an academic year, I put it into XDisk, and I know I'm going to pull that data down and put it into XDisk. I'm going to compute on it, and then I'm going to move my output out to some other place and keep that. And then when XDisk expires, I'm just going to let it blow away because I have that input data somewhere else in the world where I pulled it from. And I don't need to keep a hold of that input data. I might need to keep all the intermediate data, and I might need to keep the final data, the output. But I'm going to move that somewhere that'll last, 5 years or 10 years. I'm going to back it up in 2 different places. None of the storage on the HPC is backed up. So again, it is very much a computing and an analysis environment. There's not all of the niceties. We have a little over 2 petabytes of data that's actively being analyzed. It's about 2.1 petabytes. A petabyte is 1,000 terabytes. So we have, 2,100 terabytes of data that are being worked on from the 960 active users that we have in a year. So the trouble is the HPC storage is really expensive. It's about $130,000 for 130 terabytes, and so about $1,000 a terabyte, give or take. And so we always have to be rotating, any data that you want to keep a hold of, but you don't think you're going to analyze, go ahead and move that off of the HPC and put it somewhere else. Like I was saying before, we're working on creating centralized research storage options for researchers. We're doing that work now. And one of those efforts is the data enclave for controlled PHI, which is kind of like your HIPAAs, your human identifiable type data. And so those will hopefully roll out sometime this year, and that'll be a multi-year effort. So they'll get refined because we're kind of creating things from scratch, and so that'll be ongoing projects, but will be available hopefully sometime this year. So that's storage. Again, you can ask for jobs, interactive or batch jobs, depending on what kind of work you want to do. You can log on to any of the clusters that we have through a Unix shell. Or this is what I really want to do now, and we'll kind of play around with, and then I'll go ahead and take questions and other things and see what y'all want to play around with. But basically, you can ask for an interactive app, which will create an interactive job, get whatever computing resources that you're asking for, install that software on it, and then present you the interface. So, the Python session was using Python and Jupyter. Almost everybody in R uses RStudio. I know a few people who are like base R all the way, but almost everybody uses RStudio. So I'll show you what that looks like first, and then I'll spin up a Jupyter notebook and we can play around with both of them. So we also present like information about what's going on, if we have maintenances or if we have other things going on. So this is this is a good place to come in and get kind of heads up. So in this form, we're just going to tell it how many hours we want to run. So maybe I'll put 2 here because I'm going to do this as a demo. You tell it how many cores you want. On Puma, we have 94 cores per node. We technically have 96, but we keep 2 of them because there's so many processes. We have to keep 2 cores just to process the processes. Yeah, say that 5 times fast. So I don't know, maybe I'll ask for 10. And so that's already bigger than a laptop that I have in front of me by a hair. And we also have GPUs, so you can ask for up to 4 GPUs. We have each of our GPU nodes have 4 V100Ss. So there's a lot of workflows for GPU analysis, again, mostly for machine learning and deep learning and other kinds of things, but a lot of image analysis as well, where you can get 4 GPUs and actually dole out tasks to each of the 4 and make your analysis, 4 times faster or thereabouts. So sometimes people like to, if they know that they can use 4 at a time, they like to use 4 at a time. And that, you can do that here. I'm going to skip that because GPUs are always in hot demand, and I don't want to take up something that the actual community is using for a demo anyway. And then your PI group is going to be your research PI. The way that you can check your groups is if you log into portal.hpc.arizona.edu. You can get almost all the information you need from this user portal. So I'm actually technically a PI because I run the machines, even though I'm not faculty. I'm the one exception. So in my research group, I have a bunch of people. So all of these people, anytime they run a job in the HPC, for their group, they're going to put in my net ID. And 90% of the PIs, they just use their net ID, and that's all they use. Some of them like to call it cool things. So like this is a star omics group. Thank you. I have an HPC and Viz team, so I give them different times on the machine. There's lots of we have a dark energy analysis group that has an associated name that's kind of funny and interesting. So if you need to know what group, just come here to your user portal and you'll be able to tell. So for me, I am my own sponsor, so I'll put in Joyce 3. And this is something I'll point out too. There's a couple different queues. There's high priority, there's standard, and there's windfall. And they get put on the system in that order: high priority, standard, windfall. So I'm going to select standard, and then I'll explain these queues as we wait for it to launch. So I'm just going to press the button. And basically what it's going to do is it's going to go to the HPC and say, hey, Blake wants 10 cores for 2 hours. Can we fit that on there? He's going to use his standard time. So I'm going to let that cook. Well, let's go back to that form, and I'll explain the queues to you while we wait. And this one, maybe I'll do 24 hours, and maybe I'll leave that at 3 cores, everything else. But the queues, everyone in the community gets standard allocations. That's why it's called standard. Every research faculty at the University of Arizona, regardless of where they are, can get access to the supercomputers. When your faculty signs up, they get 7,000 core CPU hours, core hours on Elgato. They get 36,000 core hours on Ocelote, and they get 70,000 on Puma. That's each month. So you get about 113,000 core hours each month on the supercomputers for free. Some groups do nothing but computation. So they'll choose to actually purchase equipment on the machines. So that's the high priority time. Most groups don't have that because they don't want to spend money. They just want to use the free allocation. And that's plenty fine. The way that the high priority works is those computing groups that want to invest in their computing infrastructure will buy the cores. If they're not using their cores, then we can schedule other people's jobs on those cores and run jobs there. So it helps the community. It also helps the researchers because it's really cheap computing. And if they try to go to somewhere else and pay for computing, it would be orders of magnitude more expensive. So it's kind of it's a win-win. The university research computing community gets access to a lot more compute than they would normally through when people buy in. But then also those people who have bought in, get a higher priority queue, and that's how it works. So basically, it allows them to run jobs on their own equipment immediately. And anytime they're not doing that, even if they were using their 100% time, then we're not out anything because that was all free stuff anyway for the rest of the community. And hopefully that makes sense, but I'm happy to go into that one more. Windfall is what you use after you've run out of standard. Standard jobs will get scheduled before windfall jobs. But a lot of times people will burn through all their standard hours in a month, but they still want to do computing. So think of windfall as kind of like a waiting queue. Like if there's free time on the computers and nothing's going on, we'll go ahead and schedule these windfall jobs. But if the computers get busy and there's a lot of people using standard jobs will actually kick windfall jobs off of the computer and they go back into wait. When that happens, if your job doesn't save its output every so often, then you'll just lose whatever is going on. But we'll reschedule it for you and rerun it. So sometimes when you put a job onto Windfall, maybe it'll run 10 different times because the bit system's really busy, but eventually it'll complete. And so, but there's no associated allocation. You can use as much Windfall as you please in a month. It's just a matter of like whether you can, whether there's free resources. The systems always sit somewhere between 85 and 100% utilization. We have a very busy, a very active computing community here. And so there are people who accomplish a lot on Windfall, and there's also, folks who are like, my job gets kicked off a bunch, I'm just going to use standard and not worry about it. So, either way you want to go. And I'll go ahead, this is our Jupyter Notebook instance, so I'll go ahead and kick that off as well. And we'll see what that looks like once it's. So the other thing is what I like to do, and this is good because not all of these things get scheduled right away, right? Again, I'm waiting in the queue, the same queue as everybody else in the research community. So what I often do, especially with Open On Demand, if I know I want to work on a Jupyter Notebook for a day, I'll wake up in the morning, I'll sit down, I'll log in, I'll ask for like a day or two's worth of, a Jupyter Notebook because I'm going to do some work for 2 days. And then I'll go make some coffee and make some breakfast. And I'll just go on with the rest of my day. And then when I'm done with my coffee or breakfast, what just happened will happen. The green light will pop up and it'll say connect to RStudio server. Jupyter Notebook just scheduled too, right? And so, there's also some amount of patience is required. Our average wait time for batch jobs is about 1.5 hours, depending on the size and the length of how long they'll run. Each given month we run about 230,000 analyses plus or minus 70. So any given day, there's a couple thousand jobs on the system that are running. So there's a certain amount of patience. A shared resource like the HPC is more about like submitting this stuff and then coming back and using it later. Open On Demand tends to be a little bit faster because you're asking for like 10 cores or 15 cores or 20 cores or something like that, or maybe 2. Because I've done millions of rows worth of analyses on a 1-core instance on HPC. I do all of my metrics and assessment in HPC as well. So just as a user, a fellow user, like there's some amount of patience is required. These things are not the same as your computer in front of you. So I will also, let's jump onto the RStudio server. and it always says that, but I'm not sure why that is. I was doing a bunch of ggplot stuff and messing around. And so what's kind of cool about Open On Demand is it kind of remembers what I was trying to do before on RStudio Server, because it uses my same credentials to log into RStudio Server. So that's kind of fun. If that's not your bag, then just close out everything before you kill your job, and that's how you go with that. So it's the same RStudio that you would have anywhere else in the world. You'll notice that all my files here are the same ones that we saw over here on the HPC storage, right? So if I go back to files, I go to my home directory, there's like CC tools and HR analysis and stuff. So I was helping our HR director, and here's my, here's an intro to HPC and all these other things. And there's my UITS HR analysis and some of my other Jupyter notebooks and things. So this is on, it sits on the HPC storage. This is on Puma. And you can use the supercomputer the exact same way you would use RStudio anywhere else. And that's quite nice. Again, you can log into this from anywhere in the world. If you leave your laptop on a taxi, not that I've ever done that, if you lose your laptop, that stuff is gone. It would be a very bad day if we lost a supercomputer, because it's in a secure location, and it would require an earthquake and a flood event to take it down. And I'm willing to take those odds, right? So there's some advantages you get just out of the box by using a supercomputer, right? Those are things that I like, and I like still as a researcher, because I still play one on TV and do things and analysis. If I go, so there's RStudio. Looks pretty much the same as what you would expect. I'm a big fan of Jupyter, so for the Jupyter folks in house, let's go back to go back here. Here's my puma.hpc.arizona Jupyter notebook. So I'm gonna connect to that. And it's the same thing you would have with Jupyter notebooks on your laptop, right? I don't know, at the risk of opening up something crazy, I'll open up some random notebook I had before. Yeah, it's just fun. And I can do the same things on the supercomputers I can do anywhere else, right? And everyone does this, so I have to do this, so I will, right? It's the same environment, the same everything. You're just on a supercomputer instead of local. So, within a few minutes, you can be in a pretty similar environment that you're used to by just going to Open On Demand after you register. I'll also point out that we're always adding new apps, and we take suggestions. So we've recently added ANSYS, which is kind of an engineering workbench set of tools. And we've added MATLAB, which the engineers also seem to like. We are going to be supporting Julia at some point, because I actually prefer that over MATLAB. That's another thing. So long story short, that's the supercomputer, and that's how you get onto it. And you pretty much use it the same way. Any questions at this point, or anything y'all want to see or play around with while we're on the actual supercomputer? And I was a teacher for years, so I'm gonna wait the 30 seconds. And it's just gonna be an awkward silence if no one says anything. I'm fine with that.
Hey, Blake, if people are just getting an HPC account now, do they need to know their PI's group name in advance, or can you help them through that?
No, that's a great question. So when you register for the HPC, you actually give us your PI, your faculty member's email address, and it'll email them and say, do you want this person to be on your allocation? Yes or no, kind of thing. So you won't have to know. They can also just add you if they already have an account. They can go to their portal, and then add you here. So, like, for instance, I could add you right now to my group and you'd be able to use it, and it would set you up with an account, an HPC account, and do all the various things. We do our best to streamline the processes as best we can. That's a great question. And then anytime you log into the portal, you would see what groups you have available. Did that answer your question?
Yep, thank you.
Yeah, of course. And if you're ever in doubt, again, we're around to help, and I'll show you, places, support places here in a bit. Anyone else? Okay, well, we will go back to the slides. Now, I'll point out just a few other things, kind of concepts to know. And then I'll just hang out and we can play around or talk about specific things. Or call it early day. I know it's been a long day, so that would be fine too, I'm sure. Stop that shooting. Sure. So, to took my desktop. There we go. So, just a little bit about how these things work now that we've gotten onto the computer. And actually, let me go back a little bit and just kind of talk through what we just did with the diagram. So, again, I logged in. We saw that when I needed my net ID and password, that was the Bastion host. After that, we were on Open on Demand, which is one of the possible kinds of login nodes. And then when I asked for that Jupyter Notebook, or I asked for that RStudio instance, what I was doing is I was on the login node and I told the supercomputer, hey, I want this number of cores for this long on this account using this queue, okay? And that scheduled a job, and it basically went to the supercomputer and said, hey, Blake wants 10 cores. Do you have them? He needs them for 2 hours. And the supercomputer went, yep, here's the 10 cores, give it to Blake, making sure no one else can get at them, download the software, RStudio or Jupyter, plug that all up, configure all that stuff, and then give it to Blake as an interface with a button. And so quite a lot of things happen kind of, sort of fast. What's cool, and I didn't really demonstrate this to you, but I could later, is because we have 3 systems, Elgato, Ocelote, and Puma, we have a centralized data storage. That's where you're seeing my files. So whether I'm on Puma or whether I'm on Ocelote or whether I'm on Elgato, I have this access to the same exact files in my centralized data repository, which are the same files I was showing you before with all the different, all the random things that I have in my file system. So that sits in a central place that's not attached to any one supercomputer. And that's kind of nice because you can actually jump onto Puma, kick off a bunch of jobs and do a bunch of things, move over to Ocelote, kick off a bunch of jobs there, and then move over to Elgato and kick off a bunch of jobs there and use your allocation across all 3 systems. And you have access to the same, the same files in the same centralized place. And that a lot of users really like that, and they wind up using that. The one thing I didn't point out is the file transfer node. And so the file transfer node is just that. If you have really big, files, anything over, let's say like 100 megabytes, it's best to use the file transfer node because it's designed to be extremely fast at moving data in and out of the supercomputer. And we can go into that if you're interested, or, again, our support mechanisms can help you use the file transfer node. I just use it for any file transfer that I do. So I would recommend that you do that too. A, it'll be way faster for you, period. B, it winds up, it winds up being a more stable experience. If you're trying to transfer files from the login node, say, from somewhere out there in the world and download them to login node, that can take a lot of time. And oftentimes the connections get broken because the server out there giving you data will time out after a long time and things. So I'm a big fan of using the file transfer node. I would recommend that for you as well. And especially if you're doing like terabytes of data, you're going to want to zip those up and then move them over the file transfer node. We have a Globus license and a number of other things. So there's also graphical user interface ways of transferring data. And we can talk about that if y'all ever want. So let's go back to where I was. So the thing that actually does the thing that actually gets you a job on the supercomputer is called a scheduler, because it schedules jobs. And it literally goes down the list of all the jobs that are in queue and says, okay, can I put this onto the computer and it will finish in the time they ask for it. And it just goes through that constantly and then puts jobs onto the supercomputer over and over and over and over and over. So when you submit a job, it gets into queue, and the scheduler goes down the queue in order based off of the 3 queues that we talked about before, and starts to add those to the supercomputer as fast as it can. We actually optimize for putting as many jobs that are requested onto the computer as possible. So we actually pack and fill nodes as best we can with the jobs that we have available to us. And we're constantly trying to reach 100% efficiency. And so our scheduler is a little complex, and I won't go into all the details, right? But basically what happens is the scheduler gets a request from you for a job. It puts it into that queue, and that job waits in the queue until there's resources available. Once they are available and it matches what you need, we'll put that onto a compute node, and then it'll do all the calculations that you've asked of and run the scripts you've asked and all these other things. And then it'll output your output files, your analyses, and it also provides a output and error file. So you can always look at that and see what happened. Did the things that I want happen? Did anything weird happen? So the error file will capture any errors that are output by the compute. And sometimes it's really good to go into those output and error files and look at them and say, is there anything weird that happened in this analysis? And again, we, the community and the consultants can help with, interpreting. Sometimes errors and messages are not extremely useful, but if anything weird ever happens and it's not what you expect as far as your output, go to that error file, go to that output file, make sure that you don't see anything there. And if you don't understand what you're seeing in that error file, Google it or reach out to the consultants, and we can help, kind of navigate those waters. We'll skip the scripts. We're actually June 1 moving to Slurm on all this, on Ocelote, and Puma's already Slurm. So I'll skip the PBS stuff, but you can submit scripts that will tell us all the same things, right? Like what group are you going to use? Be Joyce 3. What queue do you want to use? Standard. This is PBS, but this is how many cores? 1. How much memory do you want? 6 gigs of memory. How long do you want it to run? 5 minutes. That's the text way of doing analyses, which we can talk about if you want to. I prefer, again, open on demand, or there's a script builder inside of open on demand that's quite nice as well, and it will help you build these scripts, and you don't have to do this from scratch. We also have some example scripts in there, and we'll skip them. You can also modify your jobs and everything else, and these are interactive jobs. Yeah, here we go. Storage we talked a little bit about. You can always look at your storage allocations either on the command line or, again, in the portal. It'll actually show you what Xdisk and other kind of storage allocations you have access to. So if I go back here and I go to my user portal, this is where I was looking at my time. you can actually look at storage. And if I do check disk quotas, it'll show me I'm using 2 gigabytes out of 50 in my home partition. I'm using 9 terabytes out of 15 on my X disk. My group, which is all the consultants and everyone else, they're using 64 gigs out of 500 and so on and so forth. So I guess I'll have access to the other groups from Susan. But this is nice because storage fills up, especially if you don't clean it out. And so if you ever get like weird errors, like can't write or whatever else, I always go straight to the storage. I mean, even when I get onto the supercomputer, I'll come and check these storage partitions and make sure I'm nowhere near what I think I'm going to be outputting. Like if I'm going to do an analysis that's going to output like 3 terabytes of data, I'm going to go onto my portal and make sure I know where I need to put that data. I can't put it in my home. I have to put it here in XDisk because I've got 5 or 6 more terabytes. So if I'm expecting 3 terabytes of output, it has to go here. It can't go anywhere else. And so I'll tell my script to put it into here, usually in a folder in here. So, hopefully that makes sense. When you're working on a supercomputer and doing lots and lots of analyses over and over and over again, your storage will fill up pretty quick. Cool. You can also do that in the text on the command line as well. Here's the slide I wanted to get to though. So there are lots of different ways to get help from us, and we're always around to try to help. 9 to 5, Monday through Friday. We are not awake at 2 o'clock normally, hopefully, but sometimes people are. There are researchers on the system at 2 o'clock. We've gotten support tickets, no lie, like Thanksgiving at 1 o'clock at night, and they're emailing us every hour on Thanksgiving at 1 o'clock at night because we hadn't responded to them yet. We have people who are on the system 24/7, 365. We had folks on New Year's, like literally during New Year's midnight, when people are either in bed or celebrating, sending us support emails asking where we were. And it's like, well, it's midnight. We're asleep, or whatever. But we're around the next day or, whatever the business days are. So that's the consulting, HPC consulting list right here. We get a couple hundred emails a week. Last year, we closed out 8,640 emails. So if you do the math, that's about 23, every day for the 3 people we have each, 3 people we have on the group. So we try to get to people same day or next day, but sometimes if there's a lot of people asking a lot of questions, it can be a day or 2 before we get back to you. So we also have written documentation, docs.hpc.arizona.edu. Like if you need to have an answer quick, it's best to look here first, just to see if you can answer your question. We have lots of pictures and how to use the system and a lot of information there. Grant writing resources, all kinds of stuff. And we'll get to you as fast as humanly possible. But we have a lot of users, and there's only 3 consultants for 1,000 users. So sometimes we'll get back up a few days. As I had said before, we have a data and visualization consultant, and they can be reached at VizLab Consult, and we have 2 stats consultants, and they can be reached there. And these slides will be available, and this recording will be available. We're really easy to find with the University of Arizona Research Computing. Quick Google will take you to all of our resources, and let us know how we can help. I, again, am leaving, but another thing that we typically do too is when researchers are starting into their research program, if you've just gotten a really big grant, or, if you've gotten, you're developing an idea for a grant, or whatever, when you're in the design phase of what research you will be doing, maybe you're putting together your proposal for your PhD, or if you're putting together, your master's thesis proposal, we also sit down with those researchers and help them kind of understand, what would they need to do to get their work done on the HPC, what kind of scales can they expect, what kind of timelines and those sort of things. So we also can give kind of research, kind of insight and that kind of stuff, because all the HPC consultants and myself are researchers, and we have varying degrees. And so we can also help provide, bridge the gap from the research side if you have like actual research questions and need some help that way. So it's not just compute, we are the research side of it too. And with that, I will also point out, this is the ResBazAZ Arizona event. So I will also point out that we have 2 weekly meetings. Right now, these are both online, and this Thursday we'll have a hacky hour on the GatherTown. I think that's been advertised in all the emails and things, and will be on our Slack channel. And as we come back to campus, and as the world kind of gets back to normal, hopefully soon, we will likely have hacky hour be at Gentle Ben's or someplace that's near campus again. And really that was designed for people who don't like mornings, but want to hang out and like kind of get to know other folks in the community, ask questions about, their project or coding or data analysis or visualization or whatever. So a group of us used to just go kind of hang out, and we got to being about 20 or 30 people each week. And it was some varying combination of people asking questions. A lot of people would come when they were starting to finish up their thesis or their dissertation. And they're like, okay, I have 2 months to finish this analysis. Like, can you help me with my code? Or it was like, how do I use the HPC, or how do I use this cloud computing resource, or whatever else it is. And then some people would just come and hang out and just like meet other people in the community that isn't their person in their desk next to them in their department. We have a lot of people who worked from home before. They just want an excuse to get out of the house and come hang out. And it's the same thing for Coffee and Code. That's in the mornings on Tuesdays. And that's for the folks who can't hang out after hours because they're busy or they got families or whatever they've got going on after hours. Or they're just not really into the bar scenes. So twice weekly, we hang out, we answer questions. If we don't know how to answer the question, we also have quite a large community of people where we can ask and say, hey, like this is something that somebody's interested in. Is there anyone out there that knows something about this? And if so, would you be interested in talking to this person? And by and large, like networking like that is a lot of fun, and you get to see cool science and other, engineering and other kinds of research going on. So there's a lot of people who just help out because they're just kind of curious about like, what are researchers doing and how can I help them? Especially the coders around Tucson and around the world. They really like to see kind of what's going on and what are the cool things that are happening. So this is an annual event, but we're not going anywhere. We'll be here Tuesdays and Thursdays for the rest of the year as well. We won't be here Thanksgiving Thursday, or if like the holidays fall on a Tuesday, we won't be there. But otherwise, we're always around. So come hang out, ask questions, be part of the community. I'm going to Alabama, so I will still be hanging out on Coffee and Code and hacky hours as long as they're remote. And if I'm ever in town, I will go to those in person if we ever get back to in-person things. So, and I won't be, part of Arizona. So you're welcome to come hang out with us too. And with that, I will take questions. And thank you for listening to me ramble on for an hour and some change. And I'll stop sharing. Yes, thank you, Gary. Gary asked, can you explain how HPC and Cypress are different or work together? Like if I have data, that's a great question. So Cypress and the U of A HPCs are different, but they're also connected. Cypress, I'll show you what Cypress looks like. Cypress is a National Science Foundation project that happens to be headquartered here at the University of Arizona. Their whole thing is providing computing resources to researchers, which is our whole thing too. They provide different kinds of resources than what we do on the HPC side. And they have a lot of interesting use cases as well. So Cypress is also free, at least for now. They provide a data store, an environment to analyze data in the data store. And they also have a number of other kind of tools that people use. Atmosphere is mostly going away or changing here soon. That's their cloud computing. But basically, to answer the question, to answer the curious question of what's similar, what's different. Imagine this: the supercomputers that we just got done talking about are in the basement of the UITS building. Cyber sits the next floor up in the data center on the second floor. And so the Cyberse data store, as well as being its own analysis environment, is really, really close to the supercomputers. So we have a number of people here at U of A that will put data into Cyberse, do analyses on Cyberse, and then when they really need to hit it with a sledgehammer, we'll move it down to the HPC, move that data down to the HPC. It's one floor you're moving it. So it's really fast to move data between Cyberse and the data store. And they'll do a bunch of analyses on the HPC and then put that all back up into Cyberse's data store. And so that's one of those kind of niceties of having a research, a national scale research infrastructure that's in our backyard or one floor above us, I suppose. There's a lot of things that Cyberse provides that we simply can't in my group, and vice versa. And so there's a lot of interesting ways to stitch those two things together. I hope that my whoever replaces me will also kind of understand Cyberse and will be able to help researchers continue doing that sort of thing. But if not, there's enough, my HPC consultants and Cyberse science analysts do understand the HPC and we have example like workflows what we're doing. So that's a great question. Did that answer that all right, Kiri?
Yeah, so basically like either HPC folks or Cyberse folks will tell us if it might be an appropriate workflow of like moving from one to the other.
Yeah, and there's different reasons to use each. So like the data store on Cyberse is a little like it's way more connected to things out in the world. The HPC is kind of locked down. So if you're wanting to move your data around and do a bunch of different things to it in a bunch of different places, putting your data in the Cyberse data store makes a lot of sense. If you need to do a lot of computing, the Cyberse can probably do it eventually. But if you really need a bunch, then moving it down, like the time it takes you to move that data down to the HPC, and then do, if you're doing, I'm not sure what kind of calculations on the GIS side of the world y'all are doing, but like, if you're doing point clouds and stuff, you're moving that to the HPC probably, because we have GPUs that can handle trillions of points in the point cloud. Cyberse doesn't really have that. So there's kind of a time and a place for all things, right? And you'll as folks start to get comfortable with having their data and having their analyses either on the HPC or in a cloud environment or on Cyberse or wherever it is out in the world, you get more and more comfortable moving it around and doing different things to it in different places for different reasons, right? And that's when it becomes really powerful. So in the case of Ariella, we found out after we did 18 million simulations that the code she had inherited from the postdoc before her was actually, it had a bug in it. And she didn't know it until she could look at the 18 million outputs. And she literally came to me one day and she's like, well, the last 6 months of computing we were doing wasn't worth anything because there was this error. And so I said, okay, no problem. We're going to go to the Open Science Grid. We're going to do your exact same analyses, but put it onto every supercomputer in the United States. And we got that same thing that took 6 months on HPC resources to get done in about 3 weeks. And the reason we could do that was because we were already used to moving it around and using different kinds of machines out there in the world. And then, like we did 18 million things in 3 weeks, which is a lot of things. So like you get into this kind of like moving things around and using different resources to accomplish different tasks, depending on what your research is and what your needs are. Does that make sense?
Yep, thank you.
Yeah, of course. So again, like in your case with GIS, like, if you get into, and I default to point clouds because I've helped Tyson do that, right? And like, that's what I think of, like point clouds are real big and there's a lot of dots, and not just any computer can do that. And so that's why he moves his stuff from the Cyberse data store into the HPC to do that, because we have the GPUs that can actually pull it off. Yeah, great question. And hopefully that wasn't an overly long answer, but and this is also part of why we exist, the HPC consultant team, and in my position as well, is every research program and every analysis that a group wants to do is a little bit different. And so you wind up having to kind of like design what's going to happen before it does, so that, because like there's not one size fits all. There's not like, go here, do this work here, that'll be fine. Like usually there's something you got to figure out, little things that you got to sort out. And that's why we exist, is to help people kind of get over those hurdles as we go along. And indeed why the community exists too. And the one thing I haven't said is I'm going to go back to my open on demand and delete my sessions, because as long as they're running, I'm taking up resources that somebody else could be using. So I'm going to delete those now that we're done. I always forget to tell people to clean up their things, but that's fine. Cool. Is there anyone that thinks that they will be doing work that will need supercomputing kinds of resources or can use these sort of things? Oh, good deal. Yeah, so I mean, if I got a couple direct messages there, if anyone wants to talk about it, we can kind of talk about what that'll look like and how it would work. Or if anyone else has another question, we can certainly field that. We got a couple minutes. I don't want to put anyone on the spot though. Talking about your research sometimes, Yeah.
Hey, Blake, this is Nasser.
Hey, Nasser.
How you doing?
Good. How you been?
Good. Okay, I have issue in my HPC. It shows here in my location here. It shows I have 503 GB of quota, and I am under Dr. Eric group, and I got emails to move the data, and I don't know if I deleted if that it cause issue for them or not.
Oh, okay. So if you got an email, it's for XDisk.
Yes.
Yeah. And so we send emails on XDisk when it's about to expire to remind you that, hey, these files are going to go away. If you want to keep them, move them somewhere else and put them onto a hard drive, or put them into, the University of Arizona has its own G drive that you can move them to. We just want to be sure that we tell you before we delete things that this is going to get deleted at this date. So that's that email.
Okay.
Yeah. It won't cause any trouble, but be sure that you don't lose anything that you want to keep.
Okay. Thank you.
Yeah, of course. And if you know that you don't need it anymore, go ahead and delete it. Then that just saves you some time and some emails and things.
But it will not cause any issue for the group. Yes.
No, shouldn't.
Okay. Yeah. Just I was scared about this point.
Yeah, and again, the storage on the HPC isn't backed up in any particular way, so it's always good to have your data at least backed up one other place. And so, yeah.
How can I move from HPC to my local machine if I want to move that?
Yeah, and there's a lot of different ways for good or for bad. There's a lot of different ways. One of the easiest ways is to use the open on demand. Here, I'll show you. So like home directory. If it's a small file, let's see. That's 622 bytes, so I won't do that one. I don't know, this one's kilobytes. Let's see if I've got something in the megabyte range. Yeah, here we go. I don't even know what this is, but I'm gonna download the thing. Yeah, you can hit download and it just gives you the normal like download window that you've seen everywhere else in the world. And that will download to your local. If you're trying to take like your entire directory off, that's where you get into kind of larger data transfers. So in our docs, this is a perfect question. The number one thing that I myself deal with as a researcher, but also that we help researchers deal with, is file transfers of some degree, right? We have some people who come to us and they're like, we need to move 50 terabytes. I'm like, cool. Do you have 3 weeks?
Wow.
You know, yeah. And I'm like, cool. You have 3 weeks? And they're like, no, we need it tomorrow. I was like, there's not a technology on the planet that will let you move 50 terabytes in a day. Like, if it, well, maybe there is. If it exists, I don't know anything about it. I would like to know what that technology is. Right? Of course, live demo about site. And get us trouble here. That would be. So this is also how it works. Like I'm always on the system and on the docs and doing things. So anytime I see something wrong, I have to ping our group. I'm going to ping them and they'll kick it and it'll work. talk about instant satisfaction. This is the thing I'll miss about my job is the instant satisfaction. When I ask a question, they kick the system and it works. Have you turned it off and on again? It's kind of a running joke, right? And IT. So when you go to our doc site, it kind of gives you an overview of the system and will point you to a bunch of different things. It also will take you to either Open on Demand, which is where we were scheduling the jobs, or to the user portal. And anytime I'm on the system working, I almost always have my user portal open so I can keep an eye on storage and things, or look at my groups and know how much time I've got left in them. Or looking at my, or I've got Open on Demand to actually do work. And that's just how I personally use the system. You might wind up using it in many other different ways. So the other thing I'll point out, and maybe I neglected to say this, like when I was using 10 cores for 2 hours, if I had used it for this whole 2 hours, I would have been charged 10 times 2 CPU hours. So 10 cores for 2 hours is 20 CPU hours. On Puma, I get 70,000 of those a month. So that's kind of okay. Hopefully that makes sense.
Blake, what about the virtualization? Or visualization?
Yeah, visualization. Mm-hmm. What about it?
Yeah, I thought it's like virtualization. That's like Cypher. It gives like a machine to have like Linux, Unix, or any kind of distribution that you can have from Cyber. Yes, Cypher. It's allowed you to have a virtual machine. Yes.
Yeah. Yeah, Jetstream does that as well as most cloud computing resources. Yeah.
But do we have that option in HPC?
Yeah, it's a little different. And so those when I created the Jupyter notebooks or the RStudio, it's not exactly virtualization because that's something that cloud, that's a whole different, and we can get into the comp size some other time. But what I will show you is what we do is we use a container technology called Singularity.
Like Docker.
Yeah, and so so Vanessa Socket created Singularity many moons ago, and basically what it allows you to do is the same thing that Docker does for, and you can actually use Docker containers inside of Singularity as well. So you can go and grab a container that's created by someone else and throw it onto the HPC using Singularity and get the same software and same everything that's inside that container. So that very much feels like a VM, because really why you use virtual machines is I just want my software already there. I don't want to have to mess with it. I don't have to install it. I don't want to have to do, whatever. And so that's something of like kind of an advanced topic. And that's something that that's something of an advanced topic. And one of the things that we're working on right now is kind of an intro to containers, because on the HPC, and can y'all still see the screen where it says Scilabs? Okay, I'm gonna go to the terminal.
Okay.
Let's actually go to, so if I go on to the actual HPC, I can do module available. I don't know, what is it now? It's I'll go to facilitate. Puma's a little different. If I do module avail, I'm getting to be old, so maybe it's time for me to leave. So one of the things we provide is, in addition to containers and you being able to run a container of any type, or well, not any type, but run containers that people have developed. We also have modules, which is kind of pre-installed software. And so, there's a lot of like actual like languages and compilers and CUDA, for GPUs and sort of things. There's also just like a lot of like data analysis kinds of tools. So, I'm a geneticist, so all the genetics things pop out. Callisto is an aligner. Jellyfish is part of Trinity, and it does alignments as well, or assemblies. I mean, Callisto is an assembler, sort of as well. There's like Beast, which is a metagenomics package, if I remember correctly. Blast, of course, is basic local alignment search tool. And Black, they just took out the search, and now it's just basic local alignment tool. Can't make this stuff up, right? So like we also on all the systems just install a lot of software that is already available so that people don't have to install it when they get on. So either way you want to use the system, you can use a container, which will be a lot like a VM that has just your software running inside of it, or you can use software that we've installed. And so maybe I want to use Python 3.6, right, in my environment. So I'm just going to copy that. And then down here, put that up to the top of the screen. I'm going to say module load that version of Python. And now I've got like which Python, it's installed Python. Right? If I do module unload, I think.
Unload, yeah.
3, 6, 3.
Oh, by the way, today I attend one workshop about SPAC.
Oh yeah.
Yeah, it's I don't know, it's kind of,
it's similar, right?
Yes, yeah, it seems to me it's to manage like the download or manage the things.
So that's exactly right. So actually what we're starting to do is all of these different analysis packages, and like this is all, we have 100 different departments that use this. So these are all kinds of different softwares that people request. What we've started to do is to change these into SPAC files so that it's really easy for us to update these as people ask for new versions. And we have there's a software request in our documentation. Refresh that. In the documentation, there's a bunch of different things, but you can ask for a software installation through the phone. It's in here. So under accessing software, there's lots of different kinds of software people are interested in. This is the module avail. Hopefully y'all can see that. Tell me if it's too small. Here's all that module avail stuff. You can ask for an installation of software here. You can ask us, hey, I'm interested in the software. Like, how does this work? That's the consult list. You can install your own software if you prefer to do that. You think that'll be faster. So we try to give, I mean, we have just so many different kinds of users and from so many different kinds of backgrounds and so many different disciplines that we try to give people options. And people are really interested in Spark for large scale data analysis. There's
Spark.
lots. Yeah, Spark's slightly different from SPAC.
Yeah, I know Spark. It's from Berkeley University.
Yeah.
I know that. Yeah.
Good deal.
What about the CC tools?
Those are available. I believe they're a module.
Module, yeah.
Yeah, let's see here. CC.
Yeah.
A lot of people use the container, Singularity containers for CC tools. The door. Are you using? Are you thinking about doing work queues?
Yeah, workflow or.
Yeah, we have a fair amount of experience with that. So that's also kind of an advanced topic. So if you're starting to think about that, feel free to reach out and we can help you design.
Okay, last things I don't know. Maybe I wanna.
Yeah. No.
Yeah. What about HT Condor?
Yeah, so Cyberse uses HT Condor to schedule their jobs. That's their scheduler.
Mhm.
We don't have that because we use Slurm as our scheduler, but there are, depending on your need for that, we can certainly figure out something. It's usually just using Slurm. They're very similar kinds of schedulers, and they do basically the same thing.
Okay, now before it was PSB, the scheduler, portable system batch, yes?
Mhm.
Now you say Slammer?
Yeah, it's Slurm. Yeah. It's kind of a weird word, and I don't know where.
I don't know.
Yeah, I read that too. So we have what I will point out is this is our doc site again, and under user guide,
Yeah,
we have running jobs with Slurm.
Slurm.
The old scheduler was PBS.
PBS, yeah, PBS.
If you go here, it'll explain, what it is, how you work with it, the kind of commands you would use, what each of those pieces mean, how you get GPUs. And then we actually have a Rosetta Stone for people who were used to PBS before and like how they can use Slurm now, because we're moving to Slurm for all the systems here in the next couple of weeks.
Okay.
So like, here's the old PBS command, here's the new Slurm command, here's the old, and so on and so forth.
It's all both is batch processing?
Interactive and batch, yeah.
Okay.
We'll do both. Slurm, we moved to Slurm because, well, everyone in the community is doing it too. And so I kind of figured if we're going to teach people something here at University of Arizona, once they graduate or they get another job somewhere else, I don't want them to have to relearn something because everyone else is using Slurm. So there's some amount of that I was just kind of like, let's move to this thing. PBS, it was also written in the 80s.
Yeah, old.
And things have changed, since the 80s, myself included. And so, starting to lose my hair and things. So it was just kind of time. Like Slurm is a bit more of a modern scheduler, and it does a lot more than PBS does. So that was the decision.
Yeah. Thank you.
Of course, it's good to see you.
It's good. Oh yeah, and I'm sorry you are gonna leave.
Well, yeah, I'll miss out, yeah, but that's how it is.
Yes. Good luck.
Yeah, thank you. Yeah, and Eid Mubarak from last week. Anyone else want to talk about something or are interested or have questions? Well, cool. Well, I'll hang out for a few minutes, but otherwise, that's kind of everything that I had for today. These systems are fairly complex, but they're also can be kind of simple to get onto, as I demonstrated. So the way that I always suggest people who are just starting out is to kind of get onto the system, try to do one analysis before you try to do 100. and really get to know what kind of things you're trying to do, and we can help you with that. And we'll, my consultant group is going to be sticking around, clearly, and the ResBaz community isn't going anywhere either. I think we're 600 strong now or something like that. So don't hesitate to reach out. And a lot of why we do what we do is we all learned this the hard way. That is to say, by ourselves. And so, my consultants, as well as and I don't normally speak for them, but I know this to be true. The reason we do what we do is because we had it hard, and we don't want other people to have to do it that same way. So never hesitate to reach out if there's something that we can answer or give you insight to, or if the system doesn't work for what you're going to do. That's that kind of like experimental design and project design side. We've designed the system to try to help the 90%, but there are people here who are doing research that that's just huge. And so a lot of what I do is help people get out to national resources. Their NSF has funded national scale supercomputers. Oak Ridge has them. There's their own kinds of supercomputers, and we can help you move out to those if you have like truly huge projects or like a consortium that you're part of. I recently, about a year ago, reached out to OSIRIS-REx, and I was like, hey, I've seen your servers, they're 10 years old. Let me help you. And so they gave me a couple things to benchmark. I ran them on our oldest supercomputer, and they ran 5 times faster than on their servers. And I was like, look, we're free. You're a massive project that's here at the University of Arizona. Like, just like, let us help you. Like, just run your stuff on our computers, and I think you'll enjoy it a lot more. So we had a number of users from OSIRIS-REx kind of jump onto the supercomputers instead of using the same servers they had been. So we're also, these things are flexible, and we can make them fit whatever research you're trying to do. And that becomes just a conversation at that point. So, don't ever hesitate to reach out. With that, I will say thank you for your time and questions and curiosity and insight, and hope to see you around this week.